Hello, everyone. Thank you for joining us today. My name is Gavin Jenkins, Managing Editor of Roads and Bridges Media. And on behalf of Roads and Bridges, I would like to welcome you to today's Infrastructure Insider Live Connect web event, part of an ongoing series of educational, professional, and developmental sessions. Today's presentation is Inline Viscosity Monitoring for Consistent Asphalt Quality. Viscosity is a key indicator for asphalt properties and quality. In this webinar, our presenters will describe the advantages of vibrational sensors for inline monitoring of asphalt and asphalt emulsion viscosity. They will describe a ruggedized torsional inline viscometer that has been successfully integrated into a network of asphalt terminals. The presenters will discuss the underlying technology of the viscometer, including those features that make it particularly robust and independent of installation position and orientation. They will also discuss the particular demands of asphalt applications, including measures that need to be taken during shutdown and startup of asphalt lines. An important requirement for remote monitoring of viscosity is the interface over which the viscosity data is transmitted. The presenters will summarize the available electronic interfaces and how they contribute to making the system compatible with existing monitoring and logging equipment. We're going to get started in just a couple of minutes, but first a little housekeeping. You will notice on your viewer that you have the ability to ask questions. We encourage you to ask questions, and we will try to answer as many as we can at the end of the presentation based on time availability. Any questions we do not get to, we will answer offline. Also, viewers of this and all the Infrastructure Insider Series sessions will be able to earn 1 professional development hour credit per session. The PDH certificates will be sent to all registered participants within 2 weeks of this event. Now, today I am joined by Dr. Joe Goodbread and Dr. Sunil Kumar. Joe Goodbread is the founding member of the team that developed Rheonics core technologies over the past 30 years. He established and directed the Experimental Mechanics Laboratory at the Institute of Mechanics, ETH Zurich. He has developed substantial IP in the field of fluid properties, sensors with 11 granted patents and more than 20 pending. He has a BSE in Aerospace and Mechanical Engineering Science from Princeton University, a MS in Biomechanics from Stanford University, and a Dr. Tekken SC from the ETH Zurich in Biomechanics. I hope I didn't butcher that too much. Early in his career, Joe worked with SRI and therefore headed the IMES labs at ETH Zurich. Joe is also a trained psychotherapist and a founder of the Institute of Process Work. He is an author of 4 books on the subject. Joe's extensive research and engineering skills form the technical core of the Rheonics products and services. Sunil Kumar has extensive experience in the sensors and energy sector, having worked in a variety of roles in engineering and research in his early career. Most recently, Sunil worked at Baker Hughes, where he led global engineering for drilling services. Sunil founded companies in the US and UK that successfully commercialized innovative products. He graduated with bachelor's in aerospace from Indian Institute of Technology, a master's in mechanical engineering from the University of California, Irvine, and a PhD in electrical engineering from Imperial College London, where he developed the SICE SP seismometer that is part of the main payload for the NASA InSight mission to Mars. He is a prolific inventor with over 25 patents and multiple peer-reviewed papers. Sunil's vision of creating sensors for fluid property measurement that revolutionizes inline process monitoring, control, and optimization serves as the charter for Rheonics. Well, I hope I didn't butcher too much of that. I'll now turn the presentation over to Dr. Goodbread and Dr. Kumar.
Okay.
Great. Thanks, Gavin, for the introduction.
All right. Shall we start?
Sure, go on, Joe.
Okay. So first of all, thank you, Gavin, for the introduction. I wish I really actually knew that guy who had all those degrees. Sounds like an interesting character. First of all, welcome to the Rheonics webinar on viscosity monitoring for consistent asphalt quality. And next slide, Manpreet. Yeah. So at Rheonics, we specialize in robust plug-and-play viscometers that are bred for the most demanding industrial applications. We manufacture to the highest standards for repeatable, reproducible, and no-hassle industrial instruments. They find application wherever viscosity must be monitored and controlled, meeting the requirements for Industry 4.0 standards for asphalt producers, transporters, and end users. Okay. So during this presentation, we're going to discuss the importance of viscosity measurements for asphalt production, transport, and application, requirements for an inline viscometer, that can meet both the rugged conditions under which asphalt is produced and applied, giving easy access to accurate and repeatable measurement data. And we'll show how these instruments are used in actual field applications. Finally, we'll discuss how inline viscometer data can be accessed and used in every phase of the industry, from production to final application. So first of all, what are we really talking about when we say that asphalt has got viscosity? And one aspect of that, you may be familiar with this experiment that was started in Australia back in the 1930s, where some professor took a glass funnel and filled it with pitch, which is basically bitumen. And then after 3 years, they broke the tip off the funnel and let it pour. So what happened? Since 1930, exactly 10 drops of this material have fallen. So what does that show? It shows that even asphalt in its solid form is a liquid. Now, we all know that because when you lay an asphalt paving down and you let cars run over it for a few years, you develop ruts. That's because the material flows under pressure from the tires. We also know that the hotter the pavement gets, the more it's susceptible to deformation from loading.
Thank you. Bye.
So what we're going to do is we're going to look not at
So these are trim, the ones that should discharge.
sorry.
I know we're gonna-
Sorry, I'm having a little bit of a technical crossover here. I'm seeing the poll in the middle of my screen here. Sorry, folks. So the important point here is not to measure the viscosity of asphalt in its solid form. We're more interested in the viscosity of the material as it's blended, pumped, transported, and eventually applied.
Honestly, I don't know.
Okay.
I don't think we have anything that helps us.
What's going on there?
What? Can we see the next slide, please? Yes. First, let's consider why asphalt viscosity measurements are important. So we'll consider why viscosity measurement is important in blending and transportation, and why laboratory measurements and standards as traditional methods for measuring and specifying asphalt viscosity. We'll look at some of the key issues and problems in using and interpreting traditional measurement methods. And finally, why these point to the need for reliable inline monitoring in addition to laboratory measurements. Okay. Viscosity essentially is a measure of how fast a liquid flows under stress, whether that stress comes from gravity or from pumping or stirring or spreading. The higher the viscosity, the thicker the fluid, and the more slowly it flows under stress. These flow properties, and therefore the viscosity, are useful for predicting how the material will age, as well as helping detect contaminants in the liquid asphalt. Since viscosity measures how the liquid flows, constant viscosity means more uniform paving. Viscosity can predict the material stability, as well as giving insight into its composition. Viscosity, Viscosity changes with different sorts of voids in the final mix, which also impact quality. Better measurement enables tighter control of viscosity, which improves performance, reliability, and efficiency of the application, all of which contribute to more economical, higher quality roads and pavements. Viscosity measurement contributes to higher quality in all phases of asphalt processing, from production through transportation to final application. During production and blending, it can assure quality of formulations, as well as supporting adjustment and automation of the processes for the most uniform quality. Viscosity measurements also reveal changes in asphalt properties during storage and transportation, either as acceptance criteria for the end users to allow adjustments or to allow adjustments in the application process to compensate for changes in viscosity. And for the end user, accurate measurement and tight control of viscosity enable optimization of the application and compaction of paving material. So now we're at poll question number 2. How is asphalt viscosity measured in your company? I'm not sure. We send samples to the lab and someone gets a report back. Or B, we use asphalt rheometers in the lab. Or C, we have inline viscometers installed in our terminal lines. Okay. Okay, so let's move on to looking at some of the traditional laboratory methods.
Joe, I just thought
Yes.
that poll was very interesting and something to highlight, that majority, 84% actually voted that it's something that they actually send it a sample to the lab and they get a report back. And this is in line with what we have seen as well. Actually, the last one, which is 0%, no inline viscometer, is exactly also something that we have seen often. And it's also perhaps the biggest reason for putting together this, discussion about it, so that we can not only talk about what some of companies in asphalt are doing now with inline sensors, but we also can understand from the audience that what are the kind of problems that they're seeing that is stopping them from using inline instruments for better quality control of their asphalt processes.
That's good. So perhaps we can integrate that into the Q&A at the end,
Absolutely.
that discussion. Great. Okay. So let's take a brief tour of traditional laboratory methods for measuring asphalt viscosity. I think maybe the most common is the Asphalt viscometer, which is basically a cup that's filled with a sample of the material and has an opening in the bottom, and the time that it takes for the cup to drain is inversely proportional. The longer the cup takes to drain, the higher the viscosity of the material. And I think this is a standard measurement. There's a few other methods, for instance, capillary viscometers, which measure the time it takes for a sample to flow through a thin tube. There are also rotating viscometers, which measure the drag on a rotating surface caused by the asphalt's viscosity. And there's also various specialized low shear methods that come closer to measuring how the stuff actually behaves in use. Okay. And here you see pictures of some of those methods. On the left, you see a capillary viscometer, and I believe at the top of the page is a Asphalt viscometer, etc. And then there's two rotational instruments on the right, and I think looks like a penetrometer on the bottom here. So laboratory viscometers are generally not really good for field use. They tend to be very delicate, they're complex to operate, and they're time consuming to use. At the asphalt terminal, you really don't, especially when it's minus 20 degrees outside, you don't want to be messing around with laboratory instruments. And another factor is that these laboratory tests typically take between hours or days before a lab report is obtained on a sample that's been sent for analysis. Okay. Oh, you've no, go back one, please. Yes. The long elapsed time period means that the viscosity report actually bears very little relationship to the material that's currently being made or pumped or applied, since there's been a lot of time for the material to change since the sample was taken. Okay, the next poll question. So what kinds of issues do you actually have with lab measurements? First of all, I'm not sure. Someone else is responsible, then I don't see the results. Second option is lab measurements are messy and I have trouble getting repeatable measurements. Or third, the lab measurements don't seem relevant since the results are from material that we pumped 3 days ago, not what's being delivered today. Okay, thank you. So it looks like the results are in. We can move to the next. Yes. So laboratory measurements have the following limitations. First of all, you need skilled technicians to do the work. They have to be trained in lab procedures. The measurements are not in real time, so the results don't reflect the state of the material actually being processed or applied. Their accuracy is limited. In spite of being precision instruments, it's not unusual to have errors of 10 to 20%, even for routine measurements. And perhaps one of the most important things is temperature. We know temperature is a major determinant of viscosity. And the temperature at which measurements are made in the lab are often very different from the temperature of the material that's being pumped or applied. These limitations mean that lab measurements are not really transferable to inline measurements, nor are they useful for real-time viscosity control. Okay. So by contrast with lab analysis, inline viscometers enable viscosity measurements that are more directly relevant to actual production, transport, and application processes. First of all, they measure the properties of the material actually being applied as it is being applied. Inline viscometers enable tighter control of material properties in all phases of processing and use. It can detect and prevent delivery of the wrong blend or material, which can be quite costly. They lower the risk of accidentally applying improper or defective material by catching the defects as the material is being transferred. And in the longer view, real-time data is essential to benchmarking operations, contributing to optimization and quality improvement of the production, transport, and application processes. Furthermore, such traceability is becoming increasingly important as agencies collect more data for environmental impact studies. So now let's take a look at what some of the requirements are for an inline asphalt viscometer. First, we'll look at the factors affecting device selection. Then we'll consider both the functional and operational requirements. We'll see how these requirements help to specify an instrument that fit these requirements. And we'll take a look at the advantages of the Rheonics SRV viscometer for asphalt viscosity management. And finally, we'll look beyond measurement to see how instruments can support real-time viscosity control. So, fourth poll question. What experience do you have with inline viscometers? None. I've never used one. Don't know. We've had a couple installed, but they stopped working, so we went back to lab measurements. They're interesting. They give repeatable measurements, but they don't agree with the lab measurements. Or D, they work so well that they are now routinely integrated into our production and transport process. Okay, and as we saw from one of the first questions, very few people in the field actually have had much experience with inline viscometers. Okay. So what are some of the requirements for an instrument that measures viscosity in line? First of all, it has to deliver continuous data streams in order to be useful for real production and quality control. It has to give immediate measurements. They can't lag behind the actual fluid being measured. They have to be free from calibration. Calibration is one of the most troublesome aspects of viscometers, and yet you can't go out in the field and pull out an inline viscometer at a remote site and do regular calibration work on it. And it should be automatic, essentially autonomous, and make its measurements silently without any need for operator intervention, because the operators are concerned with making and applying asphalt and not being measurement specialists. And finally, the delivered data should be compatible with existing data and control systems so that it facilitates rapid and efficient installation without the need for special data processing systems. In other words, it should be compatible with whatever data system is being used in your company. Okay. So what are the functional requirements? Typical measurement range is 100 to 4,000 centipoise. That's 100 to 4,000 times the viscosity of water, in case you're not familiar with that measurement system. And it has to operate over a temperature range of 40 to 200 degrees centigrade, which means about somewhat over 100 degrees to 400 degrees Fahrenheit. Okay. And what are some of the operational requirements? Well, you know the kinds of environments that these things have to work in. We see pipelines running from one part of a plant to another, or loading stuff and loading material into rail cars. The viscometer has to operate under challenging environmental conditions. And we're talking about ambient temperatures from -20 to over 50 degrees centigrade. That's -5 to 130 Fahrenheit, without malfunction or damage, including to any associated equipment like cabling and electronics. Okay. So what are the alternatives to laboratory instruments when you want to do inline measurements? Probably the best option is using vibrational instruments. So what is a vibrational instrument? It has something that vibrates, like a little reed, or a cylinder that oscillates in torsion. It twists to a very, very tiny angle. And the viscosity of the fluid that it's immersed in damps out those vibrations. So by measuring the damping of that resonant element, of that vibrator, using special electronic circuits, it can estimate the viscosity of the fluid that is doing the damping. So these types of instruments have the advantage of being relatively compact. They can be mounted in existing piping or tanks. They don't have to have very special fancy mounting arrangements. And they have fast response, which lets them deliver viscosity data real time, independently of the operator's measurement expertise. However, most of these instruments are limited by the need for frequent calibration. They're relatively complicated to install because they tend to be very heavy, and you have to be careful that the measuring element is protected from contact with other equipment, so that because it's relatively fragile and easily damaged. So given that you don't have that much experience using inline viscometers, what qualities would you most value? Repeatability of the measurements, or maintenance free, or they should agree with the lab measurements. And never mind D. Just if you could design your own instrument, which of these things would be the most important? So it looks like the repeatability of measurements is actually seems to be the most valued. But freedom of maintenance and agreement with lab instruments are also important. Okay. So let's go on. So I think we can skip this slide. I realize that we're running a little bit behind. Let's advance to the next one. Okay. Let's take a look at the Rheonics SRV, which is, we call it the viscosity technology revolution for asphalt, inline asphalt monitoring. Why do we say that? It's a very compact instrument that can fit into any existing system usually with no modification whatsoever. It's easy to install. And it has self-checking features that report back to either the operator or the monitoring system when and if the sensor needs attention. Has a very wide measurement range, and oops, sorry here.
While Joe is finding his words there, I just
Yeah,
want to
sorry.
mention that there was one key thing which we have seen often, and that is that you might have a temperature sensor, RTD, in your line. And one of the things about these sensors is that you can replace a temperature sensor with an SRV, and you get temperature because we have a temperature sensor in this, plus the viscosity value as well. So we had given it some thought that to get viscosity information, you do not necessarily need to find or do hot work to add another port for these kind of instrument.
Mhm. Okay.
Right, Jason.
Great, sorry. And one of the key features of the instrument, which goes along with its freedom from calibration, is it extremely stable and repeatable. And this is important because a lot of early and competing vibrational instruments had a bad reputation for being sensitive to vibration and shock. And when you have one of these instruments installed in a pumping line or out in the field or in a production facility or even in a blending facility, it's very hard to isolate these things completely from ambient vibrations. So what are some of the other advantages? First of all, you don't have to, with an inline instrument like the SRV, you don't need to sample and you don't need to handle asphalt fluids. So it can largely replace offline lab measurements. We'll have more to say about that in a few minutes. The readings do not depend on the skill or the judgment of the operator, which is not the case with most even precise lab instruments. The data is extremely reliable. It's repeatable, it's reproducible. You can change out sensors. If one gets damaged, and the replacement sensor will read exactly what the first one did. And above all things, it really frees the operator to focus on what they do best and their core skills of producing the best material most efficiently. Also, you can use a single instrument for asphalt, all sorts of asphalt types, from pure bitumen to aggregates all the way to asphalt emulsions. And as Sunil pointed out, it's got built-in temperature monitoring, which enables temperature compensation of the viscosity reading. We'll have a little to say about that further on also. Yeah, I think we discussed these points already. Perhaps the point that the lifetime, this has an estimated lifetime in excess of 25 years. So particularly in remote installations, where just getting to the equipment to change out a sensor can be a major cost. We believe that this fact alone will result in substantial savings in inline control. Okay. So what about implementing the solution based on the SRV? So first of all, we'll take a look at some installation options. We'll look again at the robustness and the lifetime and reliability and how these contribute to remote installation and maintenance. Okay. So first of all, where do you install these things? Here are some pictures of some diagrams of different installation options. These are all shown in pipe installations. And the advantage here is you can, as Sunil mentioned, you can use existing access ports. You don't have to do any hot rework of piping systems. And you can put it on flanges. There are different sorts of flanges available for mounting. And the important thing is that you have freely flowing material that surrounds the sensor, so you get good material exchange. And what the sensor is reading is representative of the main flow. Okay. In blending tanks, you have the option of putting it in different places. You can go through the wall of the tank, come in through the top, or mount it on a bracket on an open tank. And the SRV is available with different lengths of bodies. And as you see on the right, you can get a protective cage for it that protects it from accidental contact with other equipment or mixing blades. Now the sensor is part of the system. The other part is the electronics unit, and the sensor can be connected to remote electronics by a cable, or you can have a housing, as you see on the left, that's integral with the sensor itself. And the interfaces can be let out through cables coming from that transmitter housing. I think I don't know, Sunil, how long is the permissible cabling? I think it's up to half a kilometer. Is that right?
Yes, if you're using an EX rated sensor, then it's half a kilometer. Otherwise, you can go up to 1.5 kilometers. And so, often we have seen that customers need a few hundred feet, and that's completely fine with the sensor. And it can be a lot longer than that.
Mm-hmm. Okay. So here are some, then the question is what you do with the data. So very often this data is not just read off from a display on the sensor, although that can be done. But usually the customer will put it through a programmable logic device or logging systems or an in-house data system. And we supply this system with the electronics with a large variety of interface options built into the system. So here's a typical use case of in asphalt transportation and pipelines. You can detect when the viscosity is fluctuating outside of control limits, whether it's due to aging or contamination of the material. And it can notify the operator of out of range values by means of alarms, which can prompt the operator to pull samples for laboratory confirmation of material changes. But the main point is that it shows trends. So it allows the operator to both predict and correct problems before the material becomes unusable. Also, it logs the viscosity data, both for material traceability in the case of abnormal behavior, or for supplying information for data-driven process improvements. And because the data is available in digital form, it's easy to record and analyze using available factory data systems. So let's talk a bit about data access and analysis. The overall aim of continuous data inline viscometers is to provide easily accessible information about the state of the asphalt. An additional benefit is reduction of sampling rates, since measuring the trend between samples indicates when possible problems make sampling necessary. This is important because one of the functions, one of the aspects of laboratory measurements is they generally use standard methods. And as we'll mention a little, we'll go into a little more detail on this soon, but the SRV does not necessarily provide numerical values that are identical with the corresponding laboratory methods. So in a typical use case, you can monitor the general trend of the viscosity using the inline viscometer, and then periodically compare that with laboratory results. So you have both an indication, you can use the trend data to see how well the viscosity is tracking with the laboratory standards. Okay, and here are the logos of the various interface options that are available on, I believe, as standards with the SRV electronics. An inline viscometer needs to provide the right data channels to interface with Industry 4.0 standards. And then a side effect of flexible data interfaces is the possibility of onboard data logging and archiving, making sure the data is usable and available, even if the data flow from the sensor to the central automation system is interrupted. SRV electronics has a little SD card in there, and even if all else fails, you can pull the data off that card. So as we mentioned earlier, viscosity data is important in all phases of asphalt production during transportation and application. So if we have a continuous data stream, that means that we can optimize processes during the initial phases of operation, allowing the correlation of inline readings with laboratory measurements. We can optimize pumping, transportation, and application methods, since each of these is strongly influenced by asphalt viscosity. And finally, we can develop a global viewpoint by correlating and analyzing data across a whole distribution network for particular products. This can lead to dramatic improvements in network-wide quality assurance. Here's a sample of some actual data from an asphalt line. The total time span here is about 9 hours. For the first 5 hours, the viscosity varies between 75 and 105 centipoise, a unit that's commonly used for less viscous fluids. At 2:30 p.m., there's a sudden increase in viscosity to over 200 centipoise. The disturbance lasts for about an hour before the material returns to its normal value. Events such as these can be used to alert the operator to check for abnormalities in the process and to evaluate whether this will impact the quality of the material produced during this time. If this disturbance had lasted much longer, it could have gone on and delivered possibly defective material if the next sample was due to be pulled in 3 hours or the next day. Okay, next. A critical feature of asphalt viscosity is that it varies strongly with temperature. Hot asphalt can be mixed and pumped and transported and applied. When it cools, it hardens to a state where it can take very high loading without flowing. Therefore, a major goal in measuring asphalt viscosity is to predict its behavior at point of application from measurements taken at temperatures higher than actual use temperatures. By making measurements across a large range of temperatures, it's possible to develop a temperature compensation formula and to integrate this into the electronics that predicts the viscosity at any temperature from the viscosity at a different temperature. So ideally, if we know what the temperature compensation formula is, when the material is being pumped into from a tank, we can already predict what the viscosity is going to be at application temperature. So the current approach is to sample and lab measurement driven. So typically, I think we've been over this already, that you make a measurement and sometime later you get results back from the lab. A lot of time has passed and doesn't really reflect the material that you're flowing or processing. So we've also been over this. Okay, let's go on to the next one. So another scenario, real-time data-driven quality assurance, enables two important lines of development. The first is the correlation of inline measurements with sampling and laboratory measurement. Asphalts and its blends, emulsions, and other products are complex materials that give different measurements under different measuring methods used by different types of instruments. It is unlikely, for instance, that a Seybold cup viscometer will give the same viscosity values as a vibrational or even a capillary instrument, even at the same temperature. But the availability of continual data streams allows correlation of the inline measurement at the moment of sampling with the lab report on that sample. This allows building a model in which the equivalent laboratory value can be calculated from the inline data. A further possibility opened by a repeatable long-term inline collection is to close the loop between actual performance of pavements and other applications and the viscosity of the material used in its manufacture. Such data can help in optimizing and predicting the effect of asphalt viscosity on the long-term performance of its applications. Okay, and yes, so we've also essentially
So,
talked
Joe, let me chime in here. So basically, we're talking about two scenarios here. And both of the scenarios are coming in play because of the inline viscosity data that you are collecting. But the first one takes into consideration the lab measurements that people have done, and there is a lot of database there. And often what we see is that there is a great desire to be able to use that lab measurement, and people want to see the same values coming from an inline instrument. Now, as Joe was saying earlier, no two instrument, not even two lab instrument, not even the same instrument, typically gives you the same value. But often what happens with lab instrument is you have a trend information and you are able to use a lab instrument quite well. And it's very well established to check that you have got the right composition of asphalt. And basically it satisfies the different ASTO and STM standards. So you have a good checkbox that says, hey, this is the right asphalt, composition wise, flow property wise. So how do we make that relation between what report you got from the lab that's saying, hey, this is a good batch, and an inline instrument that is actually monitoring that batch as it is being pumped into the truck. So it is possible in those scenarios that you can actually take the measurement that you got from the lab. And yeah, so let's take an example that you basically have a report from the lab, and that's saying that it is 1400 centipoise at a certain RPM and at certain temperature. Okay, and the SRV sensor, which is in that terminal, while that asphalt is flowing across it, it gives you a value of 260 centipoise at a temperature which is around like 200, like in excess of perhaps 200 Fahrenheit, right? Completely different temperatures. Now, by using the model which is available on the sensor, you can modify this value that is being output by the sensor, the line viscosity, into a lab equivalent viscosity. So what is the benefit of that? The benefit is that SRV is a fantastic sensor for tracking any kind of change you have from that baseline. And that baseline is the number you got from the lab. Okay, so now you, instead of the SRV just giving you 260 centipoise, it will also give you 1400 centipoise and the variation in it. So it can go to 1460, it can go to 1500, it can come down to 1300. And depending on the limits you have, your operator can basically say, well, this is still within my limits. So that is the main reason that something like this can be done. It is being done by some of the customers that use the sensor. So that's one method. Now there is a second method, and we want to talk a little bit about this, because this is in certain ways very low effort but extremely high value method. Here, you still continue taking samples and running it to the lab because that you anyways need to do to meet the standards. But in the background, or like in real time, you have this sensor collecting all the data. It's going into SCADA systems. You have continuous, like every 2 seconds, you have the data of the asphalt, right? Now, this data gets collected over a long period of time, and you, as you see here, like as the data is being collected, you can put the sample, like the lab measurements that were coming back as data points here. So now your sampling might be like every couple of days, every like 6 hours, whatever frequency. That data is basically superimposed on top of this real-time continuous data. Now, once you have this, let's say like a couple of months of data that is there along with the lab measurements, you are able to create a baseline because you have lab measurements that said, well, this is all good. And there will be some lab measurements that says something is off and this is not acceptable. And your real-time data will show a certain variation when everything was good. And it will show that maybe the variation was too high when it was not good, something like this, like an outlier. So from your lab and the real-time measurement, without doing any R&D in the lab, you have been able to now create both a baseline and the limits for your asphalt product. And this, then the next step for this is that once you have system like this in place and working, now you can actually use this information to do event-based sampling. Okay, and whenever the sensor says that now I am outside of the limits that you have set from the historical data and your old lab measurements, you can actually at that time would be a good time to basically say, well, open the tap, take a sample, send it to the lab to check if we are really out of spec. And often you'll find you are actually out of spec. But when the sensor is giving you a value which is close to the baseline within the limits, you can be almost 99% sure that, well, I am going to meet my standards. And this will be validated by the normal sampling you are anyways doing, which you have to do from a regulation perspective. But that is the biggest thing, that you can do event-based sampling. You can basically every load, basically not single drop, but every, let's say 2 seconds, you have the data points. So you have full trace tracking and traceability of every load that is going out. And the biggest advantage is that if you have the ability of making changes when things are, the sensor is starting to show that the measurements are deviating, then it allows you to do that instantaneously and not wait for data points to come back, right? Good.
Well,
Joe, I think you can take over there.
okay. I think we're getting close to, we just have another 5 minutes to take questions. So I think we can wrap it up there. I think what you've pointed out some of the key concepts there. And I mean, we could make a summary, but this deck will be available to participants. So it has a more complete version of what we were delivering here, and maybe go straight to questions and answers now.
All right. Well, thank you, gentlemen. That wraps up our time for this webinar. As I mentioned, any questions we were unable to address will be answered offline. Let's get to the Q&A. We have one question for you two. How often does the SRV sensor have to be cleaned?
That depends on the operating situation. If under normal circumstances, it does not have to be cleaned. And in fact, it has a self-checking feature where there's a special mode of operation, which can be switched on periodically in the electronics that checks to make sure that the sensor is clean. So in the case that it reports back that the sensor needs cleaning, which is very unlikely, then it'll alert the operator, and then you can pull it out of the system and wipe it with a rag soaked in solvent, put it back in, and you're good to go.
So what we have seen in, we have these sensors, like some sensors which have been installed for like a couple of years now. And during general operation, when you have water fault flowing through and maybe there is a shutdown and then they reheat the line and start operating again, we have never seen the need to actually take out the sensor and clean it. And as Joe mentioned, this sensor has a fouling detector. And in those cases, we have never seen even the fouling detector basically coming in and warning the operator. What happens though is that when you have a shutdown and let's say you have asphalt, which basically is the line is not completely empty and you had still asphalt around the sensor, that itself is not damaging to the sensor. That's completely fine to leave it there. The only requirement is that before you start pushing asphalt on the terminal, particularly when the sensor is sticking in the asphalt, make sure that it is fully heated up so that it does not put any unnecessary pressure on the or stress on the sensing element itself. So till you do that, like basically the sensors do not need to be cleaned. Basically, they do not need to be taken out for any kind of operation.
Okay. Well, thank you very much, gentlemen. I appreciate it. And that concludes our Q&A session. As I mentioned, any questions will be answered offline. On behalf of Roads and Bridges Media, I would like to thank everyone for their participation in this event. Stay tuned for additional sessions in our regular series. This webinar will soon be archived at the same URL you used today, available on demand as well as at www.roadsbridges.com. Stay safe, be well, and so long, everyone.
Great. Thanks a lot, Gavin, Gerald, for the organization, and thanks a lot for the audience to attend this. And we look forward to getting back to the questions that we could not address in the session. Thank you.
Thank you. Thanks a lot.
Thank you.